Hi, you probably expected a video from Joe today, but we've decided to mix things up just a little. In case you haven't met me yet, I'm Andy Hogg, and I'm taking the last third of PHYS2201, which will focus on fluid mechanics. But as a precursor to fluid mechanics, I want to give you just a little bit of information on dimensional analysis, which is a technique that both Joe and I will use. In short, dimensional analysis relies on important variables and their units to make predictions about a system. Now, hopefully, you already use dimensions in a productive way. For example, you might check that your answers to problems are dimensionally consistent. If so, you'll already know that checking dimensions doesn't guarantee you get the right answer, but it does give you some confidence in your calculations. In this lecture, I'll introduce a more formal method to use dimensions to understand physical problems. Specifically, I'm going to show you the Buckingham PI theorem, which allows you to predict the form of your solution from dimensions alone. I'll then show you several examples which make use of Buckingham PI theorem, and that'll give you an idea of how to apply the theorem, and in particular, it'll show you its limitations. The main limitations with dimensional analysis is that it never actually gives you an exact answer, and that the answer you get depends partly on your judgment of which dimensions are important. This makes dimensional analysis somewhat open to abuse, and this cartoon shows you a good example of how you might want to abuse dimensional analysis. But I hope we're going to do better than that, and I want to assure you that if applied properly, dimensional analysis can be extremely useful. So, without any further ado, let's introduce Buckingham PI theorem. This theorem simply comes down to the number of physical variables that are important to your problem and the number of fundamental independent quantities that you have. Now, the physical variables of a problem are the dimensional variables that are important. Deciding which variables are important are critical to applying this theorem. Examples of physical variables might include velocity, which has units of meters per second, or perhaps density, which has units of kilograms per meter cubed. But you can also have physical variables which rely only on a single dimension, such as length in meters, or perhaps rely on many dimensions, such as specific heat capacity with units of joules per kilogram per Kelvin. Now, the fundamental independent quantities of your problem can be easily identified from the units involved in your physical variables. For example, mass is a fundamental independent quantity, essentially because it has units that cannot be reduced, in this case, kilograms. Other fundamental quantities might include length in units of meters, time in units of seconds, and temperature in units of Kelvin. Buckingham PI tells us that if we have n physical variables, and if these n physical variables are comprised of m fundamental independent quantities, then the system can be described by n minus m dimensionless parameters. Understanding why this is so profound is easiest with an example. So, let's revisit a problem that we already know the answer to, the question of waves along a slinky. This is a question you've already seen in workshops and for which you already know the answer. In particular, you know the most important variables: the tension of the wire, T, linear density, mu, speed of sound along the wire, c, the width of the wire, d, and the wave number of the wave, k. This gives us 5 variables, or n equals 5. But what are the fundamental independent quantities? We get these by writing down the units of each of these variables. Tension has units of kilograms meters per second squared. Linear density has units of kilograms per meter. The speed of sound has units of meters per second. The width of the wire has units of meters, and the wave number has units of inverse meters. So, our independent quantities are kilograms, meters, and seconds, giving m equals 3. n minus n equals 5 minus 3, which is 2 dimensionless groups. So, Buckingham PI theorem tells us that there are 2 dimensionless parameters which are needed to give the evolution of this system. The next thing we need to do is to figure out which dimensionless parameters are the relevant ones. Now, to find the dimensionless parameters for the slinky case, what we'll do is start out with a list of the variables and their units, which we already have. Then I'll work through the variables to eliminate units. In this case, it's easiest to first eliminate mass. We do this by dividing T by mu, giving a variable which has units of meters squared per second squared. In this case, C, D and K are unchanged, and we've reduced the problem to 4 variables and just 2 independent quantities. Next, let's eliminate time using the speed of sound to give t on c squared mu, which is now dimensionless. We still have 2 dimensional variables remaining, d and k, which can be made dimensionless by multiplying them together. This then eliminates all of our units and gives 2 dimensionless quantities. The caveat on this result is that this is not the only pair of dimensionless quantities that will work here. Multiples of these 2 quantities and powers of these quantities are also valid choices. But perhaps you're still a little mystified as to how this result can be applied. Well, let's imagine that we're interested in finding out the phase speed, Cp, of waves along this slinky. We know that this system depends on 2 dimensionless quantities, and we've written these as t on c squared mu and d times k. So Cp must somehow depend on these quantities. We write this relationship as an unspecified function, f, of these 2 variables. However, since the right-hand side of this equation depends only on dimensionless quantities, the left-hand side must also be dimensionless. So we have to non-dimensionalise Cp, and in this case, the natural choice is to use the speed of sound c. This gives us Cp on c being an unspecified function of t on c squared mu and dk. Note that this technique doesn't usually give us the exact answer, but it does tell us what the answer depends on. This might be useful for, say, designing an experiment to empirically test how the system depends upon different quantities. In this case, we happen to know the solution, which is Cp equals the square root of t on mu plus c squared, d squared, k squared on 12. If you divide through by c, you can see that the solution is in fact consistent with the prediction from Buckingham PI.